Let's say you're presented with the following problem. There are 3 prisoners, A, B, and C, and they are sentenced to death. The governor has decided to pardon one of them at random. The warden knows who will be pardoned, but he is not allowed to tell. Prisoner A begs the warden to let him know the identity of one of the 2 that will be executed, saying that if B is to be pardoned, give me C's name. If C is to be pardoned, give me B's name. And if I'm to be pardoned, secretly flip a coin to decide whether to name B or C. The warden tells A that B is to be executed. A is delighted because he thinks his probability of surviving has gone up from a third to a half, as it's between him and C now. A secretly tells this information to C. C privately disagrees with A, thinking that his chance has actually not gone up from a third to a half, it's actually stayed at 1/3, whereas C's chances of surviving has gone up to 2/3. So who's correct? So when thinking about problems like this, I like to first start off with a diagram to help organize the information. So let's create one axis, and we'll call this evidence. And let's create another axis. We'll call this the hypotheses. So, and what are the hypotheses? Well, A could have been pardoned. B could have been pardoned. C could have been pardoned. This is before we know what the warden has told us. What's the evidence? So, based off of how A phrased his statements, we could have been told that B will be executed, and this is actually what we're told. Or we could have been told that C would be executed. Notice that these are lowercase to distinguish the evidence from the hypotheses. Let's ask then the question, what's the probability that the warden would say B would be executed? Well, that's asking, what is this area right here? And notice that these areas, it's actually made up of these squares right here. These 3 squares. Let's extend these lines for a little bit. So, and let's focus on one of the lines. Let's ask the question, what is this line right here? This is in this line segment, it's in the A column. What is this line right here? Well, this is the probability that the warden would say B, assuming that A will be pardoned. This line right here, it means given, and given means that we are either assuming or we know this thing to be true. In this case, we're just assuming that A would be pardoned. So that's this line segment right here. And this line segment, well, that's just the probability that A will be pardoned. So these 2 terms right here make up this area right here. And if we extend the logic to the other columns, we would have probability that the warden will say B will be executed, knowing that B will be pardoned, times the probability of B, plus the probability that warden would say B would be executed, knowing that C would be pardoned, times the probability of C. This is a capital C. Okay. Now, if we were interested in the following question, what's the probability that A will be pardoned, knowing that B will be executed? Well, that's really asking, how does this area right here, compare to the entire area right here? So that means that we could just take this expression right here, stick it in the numerator, and then evaluate it against this entire expression. Put that in the denominator. So let's do that. So we have equal to probability that warden would say B, given that A will be pardoned, times the probability that A will be pardoned. Divide this whole expression by this guy right here. Let's make some room. probability, what one would say B, given A, times the probability of A, plus probability, what one would say B, given B, will be pardon, times the probability that B will be pardon, plus probability of Warden would say B, given that C will be pardoned, times the probability of C. And what did I say that this whole expression would be equal to? Well, that's equal to the probability that A will be pardoned, knowing that B will be executed. And this entire expression right here, it's called Bayes' theorem. So let's come over here. This is called Bayes' theorem. And Bayes' theorem is usually written as probability of the hypothesis, knowing the evidence, is equal to the probability of the evidence, knowing the hypothesis, times the probability of the hypothesis divided by the probability of the evidence. So let's use the remainder of this video to talk about some terminologies. Oops. Okay. This guy right here is called prior. It's called the prior distribution. This guy right here is called the normalizer. This guy right here is called the likelihood. And this guy right here is called the posterior distribution. Okay. So let's talk about this guy right here, likelihood. This guy, this expression refers to this area right here. One thing to note is that this is actually not a probability distribution. And you can see it, you can kind of see it from here. This area, this entire rectangle is a probability distribution, and this square only makes up a part of the rectangle. So we need to divide this area right here by this entire area of the rectangle, and that's what this normalizer is. That's referring to the entire area of the rectangle in order to get a probability distribution. So once we have this term divided by this term, we'll have a probability distribution. So we can then take this entire expression right here, multiply it by the prior distribution in order to get another probability distribution that we call posterior. Why posterior? Well, it's after the fact that we have the evidence. Okay, very good. So I will stop here for now, and I will use the next video to run through the calculation to see who is actually correct.